Hi, my name is Christina Wangan, and this is my Lab 4 of oscillations. In Lab 4, oscillation of a spring, the purpose is to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on a spring. The fundamental principles used were, first, Newton's second law to calculate the final velocity, and second, the energy principle, where the change in energy equals the work of the system. As a result, we are able to compare the predicted motion with the observed motion of the mass, as well as plot the energy changes computed in the model, such as the change in kinetic energy, the change in gravitational potential energy, the change in the spring's potential energy, and the change in the total energy of the system. We were given a video to put into the program tracker to plot the points of where the spring oscillated as it was released from rest. Next, I used the lecture lab videos to determine the values that will be used in the Python code, because the same spring is used in both the lecture videos and in the lab video. From the lecture videos, we are given the mass of the weight to be 0.402 kilograms and the average time of oscillation to be 1.524 seconds. From these givens, we are able to 1. Calculate the weight force, and 2. Calculate the spring force. In order to calculate the weight force, it's simply the mass times the gravitational force, and we obtain the value of 3.94 kilograms meters per second squared. Next, to calculate the spring force, it is just the spring constant K times S, which is the magnitude of the stretch of the spring. We're able to determine the spring constant from the equation of oscillation time equals 2 pi times the square root of mass divided by K. We obtain the value of K to be 6.83 newtons per meter. Then, to determine the initial length of the spring, I set the spring force equal to the gravitational force. This is possible because the total force of the system is 0, because the system is at equilibrium. And since the total force is the sum of the gravitational force and the spring force, their magnitudes must be equal, and mg equals k times s, where s is the final length of 0.7 minus the original length, which is unknown. The original length obtained is 0.123 meters. Then I entered in all the values into the Python code. Mass is 0.402, the spring constant is 6.83, the initial velocity is 0 because it is starting from rest, the relaxed length is 0.123, and everything is starting at t equals 0, and the initial position was found in the tracker video. Then I edited the code to input equations for kinetic energy, which is 1/2 of the mass times velocity squared, the gravitational potential energy, which is equal to the mass times the gravitational constant, times the change in y position, and lastly the potential energy of the spring, which is calculated by 1/2 the spring constant times s squared. We then use our two fundamental principles within the code. The first is Newton's second law, where the final velocity is equal to the initial velocity plus the total force divided by the mass times the change in time. In this case, F net is equal to 0 because there is no forces acting on the system. We obtain F net equal to 0 because of our other fundamental principle of the change in energy, which is equal to the work of the system. I then ran the code to simulate the model motion of the spring, as well as graph the changes in energy. The change in kinetic energy is represented in blue, the change in the spring potential energy is represented in red, the change in the gravitational potential energy is green, and the change in the total system is yellow. I then imported my CSV file that contained my data from Tracker to compare the model prediction to the observed motion. As you can see by the graphs, they are relatively close, the blue representing the model and the red being the observed. The second question asked to make two separate estimates of the oscillation periods. To find from the x position, I took the last time it touched the x-axis at t equals 8.19 and divided that by 5 because there's a total of 5 oscillations. Then for the y position data, I did a similar method, but measured based on the times of the peaks. So from time 0.76 to 8.95, that difference divided by 5 oscillations it made. From these calculations, I obtained the same number,